Welcome back to ECE 320A. We're in the last phase of Laplace transform directly. We'll be using it the remainder of the semester, but this is sort of maybe the last time we will officially be doing Laplace transforms. And we'll move into convolution. And as a heads up, if you want to plan your day around next time, Dr. Boza's schedule, you can guess. So I'll be here doing convolution and the rest of the material. So that's where we're headed. We'll do convolution. We'll do some Bode plots maybe even today relative to this interview question. And office hours, I've now tried to identify a time. We'll see how that works. I'm assuming, since this is a prerequisite class for the capstone, that you are not in Engineering 498A, which meets on Thursday at 4. But you might have other classes, but that was one of the reasons for picking that. Dr. Satam has his office hours right after this class, and he's available as well. You now have an assignment. If you're looking on D2L, it should be in the homeworks module, maybe at the very bottom, but I've identified some problems, given you the problem statements in another file so that you can now, if you don't have the textbook, you can at least access the problem statements. And that's due a week from Saturday. You should have plenty of time to complete that, and you can submit that to a Dropbox, and I will double check to make sure that that Dropbox stays open until that date. Again, the final exam is on a Wednesday, which is different than Tuesday and Thursday. Today we started with this interview question. Apparently, some of you were successful, I'll leave it at that, at getting the job. And that will actually motivate today's class. We'll look at the Laplace transform of that circuit and see what's the output look like as a function of the input, or as a function of the input's Laplace transform. Then we'll ask the question, well, what if we want to look at this for a slightly different input? Can we use the same analysis, or do we have to go back and start from scratch? And that's the transfer function. That now saves us from reanalyzing the circuit or the system. And we'll actually see that this particular circuit can provide all sorts of filtering possibilities depending on how we define the output. And that should be then also taken to inform you that for a given system or for a given circuit, you can identify many, many, many different transfer functions. There's not just one transfer function. It depends on what you've defined as the input, what you've defined as the output to produce the transfer function. And depending on how far we go, we'll maybe do some Laplace transform examples, etc. at the end. So how did you describe this circuit? What's one thing that you better have mentioned maybe if you didn't have anything else to say? What could you say about this circuit? It's second order, thank you. So we have covered that. It is second order. And what else could you maybe talk about? When given these problems, sometimes if you don't really know where to start, just start simplifying it. If you just replaced all the energy storage devices with resistors, you would say, well, that's just a voltage divider. I can solve that for the transfer function between the input and the output. Now let's say, well, let's keep the capacitor. I think I know what's happening if I just have resistors and capacitor. Replace the inductor with a short. And you know it looks like a short for low frequencies. Now you know that, oh, I have sort of a RC filter, and the outputs across the capacitor, that's a low-pass filter. Now what happens at high frequencies? Well, the impedance of that inductor is SL. As S gets bigger, that impedance gets bigger, and that's starting to choke off the current that's flowing through that series path. That's maybe why sometimes you'll hear inductors referred to as chokes in the working world. But now it's trying to block high frequencies. So those two together are sort of suggesting, oh, for this particular input and output combination, we actually might have something that is a low-pass filter in character or in behavior. So let's see what we can do relative to the analysis based on that thinking. We're now trying to inform our maybe help us as we work through the analysis. Can we feel warm and fuzzy as we're moving towards a solution? Do we now know or anticipate what the answer might be? How do you want to analyze this circuit? We want to now find the Laplace transform of the output, V sub 0, in terms of V sub I. Have we done this already in here? I'm getting my classes mixed up now. But I don't think we did this in 220, so if we did it, we were doing something similar to this in this class, but you probably like mesh analysis. Let's just find the current going through here. So if we now look at that current, I of S is now the voltage divided by the impedances seen by that source. And the impedances are all in series, and we can then say, oh, that's SL plus R plus 1 over SC. And if we wanted to get a common denominator in the denominator, we could put all of that over SC. And now when presented with that particular circuit, we can say, oh, the current in that circuit is now SC over S squared LC plus SRC plus 1. All scaling the voltage source V sub I of S. And you could have gone through that analysis in your description, for example. But now we want V sub 0 in terms of V sub I, and we already have the current. We can just multiply that current by the impedance of that element whose voltage we're trying to measure or describe across that capacitor. Or we now have V sub 0 of S is now 1 over SC times that current. We can clean that up a little bit. The SC's cancel, and we're left now with this relationship, or in fact, now if we wanted to excite this circuit with various inputs, we wouldn't have to do this analysis again. We could simply find the Laplace transform of V sub I, let's say V sub I of t, and put that in as capital V sub I of S and generate the particular output for that particular input. And because we can now do these interchanges or exchange of inputs, we actually want to define that as a transfer function. We could say the transfer function of this system or circuit is now the Laplace transform of the output divided by the Laplace transform of the input. And if we divide, now we've divided the left-hand side in the blue with V sub I, that's now capital H of S, and that's equal to what's in square brackets if we divide the right-hand side by V sub I of S. Or now our transfer function of this series RLC circuit is now given in that form. What kind of behavior does that transfer function exhibit? Can we sketch the pole zero diagram for that? Or what's in the denominator? Those are our poles. Those govern the modes of our system, the natural way this system wants to behave or respond. And those modes or poles actually depend on the values of R, L, and C. But given certain values of R, L, and C, can you now tell me what potential behavior you might have for a given set of R, L, and C? And now I'm thinking about something damped. Something damped. D-A-M-P-E-D. Don't forget the P. On the final, you may have a lot of the other circuits floating around, but now we have some kind of behavior. And you remember, right? From 220, overdamped, critically damped, and underdamped. We could have any of those for this set or for a given set of R, L, and C. So we could have overdamped, critically damped, and underdamped. If I have an overdamped system, can you now sketch in the S-plane what the pole zero diagram would look like? For the overdamped case. Can you envision the response of this if it was excited with a step input, what it would look like for overdamped? Does it shake around and get to a final value? What does it do when it's overdamped? It's overly damped, and that means it goes exponentially towards the final value. And overdamped means we have two real unequal poles or roots of that quadratic expression. So we would now have poles that might look like that. What about the critically damped case? I didn't do my spacing properly, but hopefully you'll be able to infer what I'm meaning. Critically damped, now they are real and equal. That's right at the intersection between overdamped and underdamped. We now would have two poles right on top of each other. And with that, hopefully I've now directed you into a thought process that now says, oh, underdamped, I have complex conjugate poles. Those are the three types of pole patterns, and I don't have any finite zeros. I'm not going to have any circles on any of those S-plane plots. Can we now, given some of this information, think about what we have filter-wise if I call this a filter? I now have two poles, only two poles, no zeros. What would this circuit look like in terms of its frequency response? What would its frequency response, or what's its Bode plot? There you're simply walking along the imaginary axis in the complex S-plane. You've now replaced S with j omega. And let's now look at the magnitude of this as omega starts at 0 and then grows to bigger and bigger values. When omega is equal to 0, what do you get for a value of that transfer function at DC? When S is equal to 0 or omega is equal to 0, you get 1. And then let's just say that we're sketching this for the critically damped case. The Bode plot now is being requested for something like that. And we are, in terms of the Bode plot, we're now walking along the imaginary axis, and we're basically looking up at the height of the circus tent above us when we have two poles stuck at those two X's and a rubber sheet, or the circus tent, on top. And now we're looking at what's happening relative to the magnitude. And in fact, what you will see, if this is now our log of omega axis, you will be okay in our straight line plot until you get up to a frequency of A. We'll just approximate that and say, oh, you started at a gain of 1. Well, that's 0 in dB. We'll go flat, and then once we hit those poles, those are now in the basement, those are downstairs, we will slope down, and we'll slope down at 20 dB per decade for each pole factor. We have 2, and they're both breaking at exactly the same frequency A. So now we're sloping not at just 20 dB, but minus 40 dB, because we have 2 factors at the same location. We'll get into more of that, or somehow we'll make that happen. And this is now times 2, so this is now minus 40 dB per decade. And what kind of a frequency response is that exhibiting? It's a low-pass filter. We can now subscript that H as a low pass. And there would be a reasonable answer for an interviewer's question. That's obviously more, but you could quickly sort of talk your way through something like that. Now, the interviewer might be so impressed that she might say, well, can you make any kind of other filter from that circuit? And you're on a roll, so you say, sure. Let's create a high-pass filter. And to do that, let's just change the ordering around just so that our output is still on the right, but this is giving or appearing to this source to give the same current that we had before. Here's the R, here's the capacitor, and here's the inductor, but now we're measuring the output voltage, and we're speculating that this is high pass. And is that true? Well, since I'm putting everything in the S domain, let me just make my energy storage elements represent those by their impedance. 1 over SC for the capacitor, SL for the inductor. The current is exactly the same as what we just derived. We haven't changed anything. We still have the same selection of elements in this series loop. An R, a capacitor, and an inductor. What we have changed is the particular element across which we're measuring its voltage. So that now if we say, oh, what's this V sub HP? That's now SL, that impedance, times the I of S. And we can just go back and write down what the I of S was before. That was SC over S squared LC plus SRC plus 1. Again, we can create the transfer function for this by dividing both sides by the Laplace transform of the input. We now have H high pass, or so we hope, and this is now V sub high pass over V sub I, which is now S squared LC over S squared LC plus SRC plus 1. And that's now our high-pass filter. What's the pole zero diagram of this look like? Do you see that we still have 3 different possibilities for the poles? Overdamped, critically damped, and underdamped. We can still have that. Obviously, this has been changed a little bit from the low pass. If this is now a different behavior, it better look a little different. And what's different now is we now have 2 finite zeros. And where are those zeros located? They're right at the origin. And let's just assume that we've picked those values of R, L, and C to be critically damped, and now we have something like this. Can we think our way through the frequency response behavior based on that transfer function? What happens at low frequencies? Is that transfer function well behaved at low frequencies? By that I'm saying, is it defined or is it undefined at low frequencies? If it's defined, it's well behaved. By that I'm saying, at 0, is the denominator going to 0? Because my numerator definitely is. But my denominator's okay. It just becomes 1. 0 divided by 1, that's okay. That just says we have no gain at DC. That's consistent with our high pass thinking. We're saying, oh, at low frequencies, this doesn't have any gain. And what happens at high frequencies? Now we let s go to infinity. We have s squared up top times LC, and the bottom, the large or the highest power of s is what dominates. That's s squared as well. We now have s squared LC over s squared LC. Oh, s is going to infinity the same upstairs as downstairs. The gain at high frequency is 1. That's looking okay, better, isn't it? So now at high frequencies, and what's going to happen? Well, if we now thought about the Bode plot of this, we would say, oh, we have 2 zeros at the origin. Those actually, if I just had those would be coming up from way, because the vertical axis is in dB. You never get to 0 on a Bode plot. You just keep going to lower and lower. I'm still trying to exercise my voice. I obviously am not yet in shape, voice-wise. Screaming too much. Can you hear me in the back? But this is what 2 zeros at the origin would look like. And so now we can play games with this. We have to have fun. We can think of this Bode plot as, okay, this is a party game. Yeah, really. A Bode plot, party game. We now have this frequency axis on the wall, and somebody says, can you pin the magnitude on the frequency axis? It's not quite pin the tail on the donkey, but it's getting close. So now where do we pin this? Do we just slide it wherever we want? Does it matter? Here I'm trying to sketch and in fact I'm now taking 20 log base 10 of the magnitude, and I've replaced s with j omega, so this is actually squared, and the j has a magnitude of 1. So I really am looking at that. I'm sketching that relative to log of omega. And if we do some of our logarithmic gymnastics, we can say, oh, division is like subtraction. So now I can rewrite that as 20 log magnitude of 1 minus 20 log, I'll do it in 2 steps. Do you see where the minus came from? Okay, I'll do it in 3 steps. We have this. This is now, how do I want to say it? Plus 20 log of omega. And I'm going to, well, I'll keep that to the minus 2. Is that okay? And now the exponent can come out front because of the logarithm. And these are all base 10 logs. So that now gives us minus 40. And what's log of 1? 0. This goes away. And here we have minus 40 log of omega. And we're plotting this. What did I say? You guys, would you wake me up? I was wanting to sketch this for 0 factors. What have I just sketched? Pole factors. I had a 1 over s squared. Stop me when you see that I'm blatantly in error. Okay? I've now plotted 2 poles at the origin. So now we have to go back and redo this. But I've now, that red line is not saying it's wrong. That's actually what it looks like now. If we plotted 1 over omega squared. We still pin it in the same place, so we're still okay with pinning. We can still pin it in the same frequency, but now the slope is minus. That's how I knew I caught my error. I go, wait a minute. Let's see, that's a positive slope, and I have minus 40. Do you see how log of omega, that's my independent axis. That's like x. I now have y is equal to mx plus nothing. There's no y-intercept. I now have minus 20 or minus 40x. I'm just sloping, and I'm always sloping. I never break. With 2 poles or 1 pole at the origin, 1 0 or 2 zeros or 3 zeros, those are just sloping magnitude curves. I can still ask you to play the game with me. Where's this? And, well, you can go, it depends, and that's correct. Until I tell you where this line is, when I now say that's 0 dB, now you can be a little bit, because before you could just put that plot anywhere and you could say, well, you didn't label the horizontal axis as far as where it was up or down, so you could just label it appropriately. But now that it's at 0 dB, what value of omega will be going through 0 dB? 1. That's where we would pin it. So, where was I? I wanted to plot 2 zeros at the origin. Do you see how? Oh, are we okay with that analysis? This is now 2 poles. At the origin. That's the Bode plot. And what's the slope? Because if I walk over here and this is omega equal to 10, that's 1 decade. I've now transitioned across 1 decade of frequencies. What's my red line going to be at, value-wise? Well, you could just plug in log of 10. And what's log of 10? 1. Multiply by minus 40. You better be at minus 40 when we're at omega equal to 10. We're going down at 40 dB per decade. Yes. Where did I get 1? I don't know. I just grabbed it and hope nobody asked. No. Where did 1 come from? I'm guessing you're meaning the omega equal 1. So now I was looking at minus 40 log of omega, and I'm asking, where does that quantity equal 0? That's where I will cross that 0 dB line. And log of 1 is 0, and that's where I wanted to pin that slope. Now I have omega equal to 1 going through 0 dB, and I'm trying to help you see why that slope is the way it is, that it's sloping at minus 40 dB per decade. Now I've tried to say that if we went down here, this value is in fact minus 40 dB. And if I went over here to 100, and I went all the way down here, again to the red line, what's that value? Log of 100 is 2. 2 times minus 40, minus 80. And I'm going down 40 dB per decade. This better be minus 80. what is it up here? Suppose, so this is omega equal to 1. This is now omega equal to 0.1. Here's omega equal to 0.01. 2 decades before omega equal to 1. What's this value? Question? I know, I've confused you. I wanted to focus on this. For whatever reason, I got sidetracked and just started with that. I should have started with this. I haven't yet. I haven't even gotten there. So I went on a rabbit trail. So now we're doing 2 poles at the origin. Sorry. Now I'm chasing that rabbit. I better catch it quick. So help me. What am I magnitude-wise at 0.01 in frequency? I'm at 80. So this is now at 80 dB. So that line, if I just had 2 poles at the origin, I could draw a Bode plot of that's magnitude. It would cross 0 dB at omega equal to 1, and it would be sloping at minus 40 dB per decade. Now to do the zeros at the origin, 2, I just flip that. Now it's coming up from the bottom, and it has a slope of plus 40 dB per decade. Can I convince you of that? Here's what, unfortunately, I was chasing rabbits, and so I didn't start with 2 zeros at the origin. That's what I wanted to do. I wanted to start with s squared, and for whatever reason, usually because we play with poles. We play with poles more than we play with zeros. So it's more common to be sketching pole factors than zero factors. But for a Bode plot, we need to be able to do both. Now we're looking at 20 log of the magnitude of j omega squared. Or this is now 40 log of omega. And we're sketching this relative to and a lot of times we just get sloppy and we just label the horizontal line omega, but it's really a logarithmic axis. It's log of omega. We now want to sketch this. Do you see that at small frequencies, that's really, really small? At 0, it's well, we never get to 0, do we? So now we look at omega equal to 10 to the minus whatever, 10 to the minus 6. Then we're at minus 6 times 40. We're at minus 240 dB. Whew, that's way down there, but we're coming up. And then when do we cross 0 dB? If we now label this, and I say here is my sketch, you can now confidently state that that's omega equal to 1. That's where we cross 0 dB, and we are sloping at 40 dB per decade. That would be if we just had 2 zeros at the origin. What do we actually have in this high-pass filter? 2 zeros at the origin and 2 poles, either overdamped, critically damped, or underdamped. It depends on R, L, and C. Are we comfortable with what I'm providing you information-wise? We're trying to convince ourselves that this is a high-pass filter. Yes?
Can you substitute omega j for s like whenever you want?
So can we substitute j omega for s whenever we want? We do that when we're interested. We make that substitution when we want to know what's the frequency response. The frequency response is really how does this circuit behave for particular sinusoids. We're now walking up the imaginary axis, and each location on the imaginary axis corresponds to a sinusoid. I go up to omega equal to 1/2. I now have a sinusoid with omega of 1/2. So now if I would say, oh, let me excite this system with cosine 1/2 t, and just let me see what happens to its magnitude and phase. That's its frequency response, and that's what we're plotting here in terms of its magnitude. We'll do the phase when we do Bode plots. But every time you have a linear system and you excite it with a sinusoid, the output is going to be shaking at what frequency? If I excite this system at omega 1, what am I going to see on my oscilloscope at the output? What frequency? Omega 1. It's a linear system. I excite it at omega 1. Everywhere in that circuit is shaking at omega 1. At that output, I want to know how has the magnitude changed and how has the phase changed. The magnitude tells me how that sinusoid has either collapsed or expanded in amplitude. The phase just tells me how are my peaks aligned with the input peaks. That's the time shift, but we denote it by phase, but we can convert it back into a time shift if we want it. Yes?
Like having the output at the same frequency as the input, is that only for steady state, or could the transient part of it?
So now what the question is do we have to worry about transient or steady state relative to what we're seeing at the output? What we're assuming when we have a frequency response is the transient has decayed, and that only takes 5 tau, so it's not that long, and we're comparing sinusoidal steady state output with the input. So we are not worrying about the transient. It's something. Actually, what is that something? Oh, won't you want to be sorry you ask? Today in 220 we were talking about sinusoids, and I said I was trying to convince them of sinusoidal steady state, and I said, well, we don't have to wait very long until we get into sinusoidal steady state. I hit a low pass filter with a sine wave, that's the blue, and I measured the red. And do you see where the transient is? It's less than 0.1 or 100 milliseconds. That's as long as we have to wait, as a tenth of a second. And then we're in steady state. Obviously, that transient interval of time depends on the values of your circuit elements. But in this case, my R and C time constant were such that it was 0.02. So 5 of those gave me a tenth of a second. Do you see that it took a little bit of time for the red curve to finally get in a steady state? That's the transient. We're neglecting that little time, and then we look and we say, oh, what's the magnitude? Do you believe me now when I say the red, the output has been reduced in magnitude? So now that would be lower than 0 dB in this case. 0 dB would say, oh, the gain is 1. The output has exactly the same magnitude as the input. And that's what we would have for a low pass in the passband frequencies, is a magnitude of 1 or 0 dB. Here, we're down to what? About 0.707. And are the peaks aligned? Or the crests align? Is the blue peak on top of the red peak? The red peak is delayed a little bit, isn't it? That's our phase. That's our phase shift. That's why we need to know what's the magnitude. That tells us how much we've collapsed or expanded. What's the phase? Well, if my phase was 0, then I would be peak to peak. Here, my phase, I have some delay. My phase is negative some angle. Any more questions? We'll come up to another lecture somewhere. I don't know. That happened today, or I probably wouldn't have remembered. Just saying. Other questions on that? Okay, somebody released a bunch of rabbits into this room before lecture, and I'm chasing them all. Where were we? Good, I'm on the correct page. We are still trying to convince ourselves that this is high pass. Do you believe now the 2 zeros at the origin, what that Bode plot looks like? I'm finally back to zeros at the origin. Thank you for your patience. That now gave me this. What happens now if I say, well, let's just, for argument's sake, locate those poles to be critically damped. Just so they're easy. They're at the same location. They're at the same break frequency. That makes it easier to sketch. Now, if I have a high pass, I'm now saying that I'm looking at this type of well, let me just do it this way. That's now my high pass filter. I hopefully have convinced you that for low frequencies, the top dominates. Actually, I'm going to be sketching this in time constant form, so I'm assuming that I now have the constant term normalized to 1. And here, just to keep things clean, I'm not even worrying about the gain anywhere. What I've said is I'm now coming up here like this. But what happens at that particular frequency? Bells go off. Besides bells ringing, you're going to ring my bell if I'm not careful, right? Anybody have gloves? Boxing gloves? Ringing my... I'm not getting into the ring. Where are we? Chasing another rabbit? No, we're trying to finally get this high-pass filter sketched, Bode plot. What happens at A? If I just had this, what would it look like if I was just sketching that? What would that look like? What does it look like for low frequencies? Put S equal to 0, and what do you have? 1. When we get to the break, what happens? Now I'm actually sketching a low pass. Hint, hint. This now goes down. And it's going down because we have two factors at minus 40 dB per decade. We now said, oh, let's change that, and now we have this. Do you see that we're coming up from the bottom because of the 2 zeros at the origin? And then at A, Actually, I should have probably made this, maybe I should have accounted for the gain, because now I want, at high frequencies, I want this to look like it's 0 dB. So can I, well, I'm doing my own gymnastics up here, but do you see that that's now what we have? We were coming up at plus 40 dB per decade. And then when we get to the poles, we were going up at 40 dB per decade. The pole factors give us a slope of minus 40 dB per decade, and they kick in at A. After A, those two slopes cancel each other out, and the only slope that we have in the whole diagram is what was coming up from bottom due to our zeros at the origin. This will become more clear as we do Bode plots later, but I thought let's just plant the seed. We're still in that interview. I've now taken off my jacket. I've started to loosen my tie a little bit. Whew. And she goes, "Are there other filters?" Have to loosen the tie a little bit more. Now what happens? Suppose we now say, what about a bandpass? So now we just, again, we're going to put the term that we want over on the right, but the series combination looks the same. Here's R, here's 1 over SC, and here's SL. We now want this, and this, we're speculating, is a bandpass. Our total impedance hasn't changed. That's still the SL plus 1 over SC plus R. And to get the current, it's the same. And so now our bandpass voltage is just R times I. And I was SC over S squared LC plus SRC plus 1 times V sub I of S. Or our transfer function now for this bandpass filter is that just like the high pass? It's similar, but now make sure I've done the algebra correctly. What do I now have? The denominator is the same. It's the same circuit. The denominator is not going to change. The numerator has changed. What's different now? We now just have 1 0 at the origin, not 2. That means then that in this plot, we're coming up at what slope from the bottom? Just with one factor, this is now plus 20 dB per decade. And what happens when we kick in the poles. How much slope do we get? We get minus 40. We now have plus 20 minus 40. The net slope is minus 20. Now we are sloping at high frequencies, and the slope is the net of plus 20 minus 40. And that those slopes are supposed to be reflections of one another. That's still terrible, but you get the idea. It's hard to see when that still doesn't look like the same, but it's supposed to be the same slope, just in the other direction. And that's passing a certain band of frequencies. That's our band pass. If you're still with us, some of you have probably already checked out, said, may I be excused from this interview, but let's go one more. We can now do a band reject. This is probably what would happen after my interview, is the rejection letter. But we're now rejecting certain frequencies. And to do that, we have the same three elements, but now we are actually measuring across two. Here's V sub I, here's R, here's SL, and here's 1 over SC. And this is now plus V sub, well, this is now the band reject filter. And what does it look like? Well, now we have V sub band reject is the impedance that we are pushing that current through, which is SL plus 1 over SC times the current, SC S squared LC plus SRC plus 1. If we combine those two terms in the numerator, the SC cancels the SC in the last term in the first term, and we get S squared LC for the first one. So now we have S squared LC plus 1 over S squared LC plus SRC plus 1. And just this little in brackets, this is our band reject filter. If we assume critically damped poles, they will be on the real axis, real and equal. What do we have happening up in the numerator? We have two zeros. It's a quadratic factor. Now if you set that factor equal to 0 and solve for S, that's where your zeros would be. What if we do that? What if we look for the zeros in this particular numerator? We say, okay, here's the numerator. It's now S squared LC plus 1. We set that equal to 0. Where are the zeros? right on the imaginary axis at that natural frequency, 1 over the square root of LC. We now have a slightly different pole zero pattern, obviously, since it's supposed to be giving us a different filtering behavior. We now have a 0 there and a 0 there. This one's at J, 1 over the square root of LC. And this one is minus J, 1 over the square root of LC. And if we have critically damped poles, those are over there. Can we understand the behavior of this transfer function by just doing sort of our thought experiments before, looking at extreme values of S? What if we look at small values of S? What's that transfer function assuming as a value? 1. So at low frequencies, it's 1. 0 dB. At high frequencies, what's happening? 1. What happens between those two extremes? Well, we are walking up the imaginary axis trying to plot this. We fall into a 0. Right? Anybody else want to finish? We have a thumbtack, don't we? We've tacked the rubber sheet down to 0. We were 0 dB low frequencies, 0 dB high frequencies. We went to 0 at 1 over the square root of LC. It's rejecting that band. Now when you see a band reject filter, all you're going to think about is somebody tripping, pretending to trip. So now we have this. We had nice there, that was 0 dB, nice there, and then we went down. We went to 0, and we never get to 0 on a logarithmic plot. Does this look like we're rejecting a certain band of frequencies? This is our band reject behavior. We're not rejecting bands on a band playoff or something. This is a frequency band that we are rejecting. Questions on that? Do you see how many different circuits we could create or transfer functions? Now, one circuit gave rise to 4 different filters. What kind of a filter was that? Here I'm asking for a different response. I'm wanting, is it passive? Is it active? It's passive. We don't have any active devices. We didn't need to energize anything for that circuit to work. We just needed to go to Josie and get some inductors and capacitors and a resistor. And then measure the appropriate locations to get our low pass, band pass, high pass, and band reject characteristics. From one circuit, we could get all 4 filter types. We will eventually, well, what we've been talking about, I'm trying to now provide the marketing for next week's material. We're going to be talking about Bode plots, but before we do that, we will be talking about convolution. And convolution, I may not derive the convolution integral. We may just do some examples. Just so you get used to the mechanics of convolution. We are going to flip and slide. You thought today was fun. Wait until next week. But what if I now wanted to say, you know what? I have some waveform. Suppose x of t looks like that. And you go, well, if I could Laplace transform it, I could just multiply h with x. Now do you see how you can get an output? Can't get anything now. But now the beauty of the transfer function is the fact that if you have a transfer function h of s, if somebody gives you an input, you can now find its Laplace transform, use that to obtain the output simply by looking at the product of the transfer function with the Laplace transform of the input. Were we okay with that? We were essentially doing that with these filters today. You give me an input, x of t, I can take it into the Laplace transform, and then if you want the output y of t, you can now inverse Laplace transform capital Y of s. What if somebody now gives you some crazy x that maybe you don't feel comfortable Laplace transforming? This is what it looks like in the time domain. Well, now, if we know how that system responds to an impulse, and do we? If I know the system has a transfer function, of h of s, do we know now what it will look like or what the output will look like if I hit the system with an impulse? Now my input is an impulse. And what's the Laplace transform of an impulse? Don't force me. It's 1. The sifter, remember? So now if we wanted to know what's y of s when we have an impulse, which is now 1, do you see that we could find the impulse response in the time domain by simply inverse Laplace transforming the transfer function? Since it's just the inverse Laplace transform of capital Y, now we're specializing it to an impulse input, which has a transform of 1. We now want y of t when the input is 1. Well, that's just the inverse Laplace of capital H of s, which we call little h of t. And we call it the impulse response. Now, with that impulse response, we can, in the time domain, via the convolution integral, figure out what's going to happen to any generic input signal x of t. We just convolve the x of t with the h of t, and we'll have the output, y of t. And that's where we want to go for next week. What I wanted to talk about even today was sort of the bridge into the next week, which is active filters. What would happen if we put this device what's the transfer function of that? Let's do it in the frequency domain if I'm now talking about transfer functions. Here's V sub I, here's V sub O. Now if I know the impedance of that, that's 1 over SC. The impedance of that is R. Do I have negative feedback? Yes. That means I can assume that my inverting and non-inverting terminals are the same, or the inverting terminal now is 0. I could perform KCL. Now what I'm doing is, let me just generalize this to say this is Z1, and this in the feedback path is Z sub 2. I could now say, oh, V sub I over Z1, that's the current in from the left, plus V sub O over Z sub 2, that's the current going to the right, or coming from the right, going left in the feedback path. That's KCL at V sub n. I can solve that for V sub O. And Z sub 2 was 1 over SC. Z sub 1 was R. So that the transfer function of that op-amp circuit is an inverting integrator. 1 over S is integrating. RC, if we just pick those to be 1, I now have an integrator. What I was wanting to show you was if I now applied a step to that integrator, what's going to happen at the output? If you integrate a constant, what happens? So if you differentiate a constant, you get 0. If you integrate it, you just get this ramp of t, correct? It's an unbounded. So you put in a bounded input and get an unbounded output. Just wanting you to see that you now know how to inverse Laplace transform 1 over S squared, where one of those S's is from a step, the other is from the integrator. That gives you t at the output. We'll pick up somewhere there. We'll try to find some rabbits next week.